Welcome to the 24th Annual Capital Conference, virtual edition. It's our goal that each of our conference sessions is about an hour in length, although we may go a little longer or a little shorter with some sessions, depending on question and answer, that sort of thing. This session is Calculator Applications Scaling Problems, presented by Dr. Dave Bourell, our State Contest Director for Calculator Applications. And Dr. Bourell, thank you for being willing to share your time, your knowledge, and expertise with our attendees in our this new adventure for our conference format. And I will now turn it over to you.
Great. Thanks very much, David. I appreciate the introduction. Hi, everybody. It's good to see you, even though it's under this strangest of circumstances. One thing I'd like to say before we get started is David mentioned that we have this an extra session, a problem-solving session set for July 13th at 1 o'clock. And my goal there really is just, it's really to work problems that, that maybe have been nagging you either for a long time or more recently. But my plan is I may come in with one or two problems I picked, but I think it'd be a lot more interesting if, if we had problems that were, real problems that you've had issues with in the past. So I would encourage you, if particularly if you have that a list or some problems that you'd like to see worked, if you could just email them to me. I think my email address is on the UIL website, or you can Google me. Google my name. I'm sure I'll pop up with an email address at the University of Texas at Austin, and that'd be really helpful. And it gives me, while I'm happy to work the problems cold, I mean, I do that all the time. It'd be a little slicker if I knew what the problems were beforehand too. But either way is fine. I don't mind stammering around with the problems either. So either way works. But it'd be nice to it'd be comfortable to me if I had maybe a few problems beforehand, or you could even send them to me now. Put them in the chat room, and I can get those before the session's over. Okay, well, let's talk about stated problems. I wanted to mention, first of all, that everything that I'm going to be talking about today is more or less in the contest manual on 5 pages from page 53 to 57. And I would also mention, maybe for those of you that may be new to the contest, that the scaling, this type of problem we call scaling problems, is on every UIL test that I write, on every test that I write, whether it's for UIL Invitational, I do a few for TMSCA as well. Problem 46 is always a scaling problem. So you're guaranteed on every official test, every test that I write, that the problem 46, that you're going to see one scaling problem on every single test. So it's absolutely, hands down guaranteed that you will see that. So let's talk about scaling problems. Basically, what it deals with is the way it's cast is it's dealing with objects that have the same shape at different sizes. And I show 2 down here at the bottom, this sort of hemispherical cylinder thing. Although, as we will see before the session's over, really what it deals with is any relationships that are proportional. And so you will see, for example, my classic example there is I have problems that deal with, with baking, like how many cups of flour do you need, to make so many certain size cookies and things like that. That's, I guess you could sort of think of it as a kind of a geometrical kind of problem, but it's dealing with proportions, as we'll see. So again, the scaling, it deals with geometrically similar figures, and that's again figures that have the same shape at different sizes. And the advantage of using scaling principles is that the calculation is much simpler than what I call a brute force approach. I'm actually going to do a brute force approach here and show you basically how much time can be saved. I'll do that in just a second. And then basically the simplification that we get from using scaling principles arises from the elimination of the necessity to calculate a constant of proportionality. To brute force the problems, we have to get that constant of proportionality. But when we use scaling principles, as we will see, the constant of proportionality cancels out, and so we don't even have to bother with it. So that's where the great advantage comes. And as the geometries get more complex, coming up with the constant of proportionality becomes equally more complex. Okay, and of course this applies to two-dimensional and three-dimensional objects, but also as well, as I mentioned, to general proportionalities. We'll see how that works. Okay, so let me use this example to show you the advantages of scaling. What I've got is a square with two square pyramids stuck on each end of it. I have two different sizes, and what I want to do is I have the information on the volume of the smaller figure here. It's that basically is given with enough information to completely define it. This is a cube with two square pyramids. And then on the right side, I changed that 0.281 to 10 on the overall length. And the question is, what's the volume of the larger one? Well, the hard way to do this is what I can do is the following. I can label the square, give this the cube side dimension A, the height of one of the square pyramids, and we're assuming that the two square pyramids are identical geometrically or congruent. So that height is B and the overall length is L, which is obviously A plus 2B. Well, what we can do is I can write an equation for the volume of this thing, and it looks like this. So it's basically twice the volume of the pyramids, which is third the area A squared times the height B. And then I add in A cubed, which is the volume of the cube. Well, what I can do now is I can, to simplify things, I can define an alpha to be A over L, and that, of course, is given. That's going to be 0.288. And it's 0.288 on the small figure. It's going to be 0.288 on the large figure, right, because they're geometrically similar. And then the beta is, I'm going to define to be B over A, which is given from the small figure is 1.2 or so. So we have that as well. So what I can do is I can take my volume formula and I can recast it this way by writing it as in terms of A cubed. So I multiply and divide both sides of the pyramidal volume by A squared, and then I can do some rearranging to get my B over A. And what I wind up with is this 2/3 beta plus 1 times A cubed. So beta is a constant. So the stuff in the square brackets on the end of this thing is a constant. That's my constant of proportionality, which I could calculate. And then I have A cubed. So I'm writing the volume as a proportionality as a function of a side dimension A cubed. Well, then what I can do is I can turn that, I can change out A for L by multiplying by A over L, by basically multiplying and dividing by L cubed, which you see on the first part there. And then since A over L is my alpha, I roll that in. And eventually what I wind up with is my volume is equal to this constant of proportionality K, which turns out to be 0.034367, which I've calculated. It's what's that red, it's that red term, 2/3 beta plus 1 alpha cubed. And I write my volume in terms of L cubed. So now since my L is 10 for the larger figure, I just multiply by 10 cubed and I get 43.7, and that's the answer. So this is sort of the brute force way. It involves calculating that constant of proportionality K. So there we are. So now what we can do to do it using scaling principles, which I'll be talking about in some detail in just a second, what I can do is I can write the volume of the small figure, which I just write by substituting the numbers. It's 3 ball 9 6 something. And then what I can do is I can start with sort of my endpoint from beginning, and that is to say, I can acknowledge that the volume of this thing is going to be equal to a constant of proportionality times L cubed. If that's the case, then I can write a ratio that says the large volume ratio to the small volume is going to be KL large cubed divided by KL small cubed, and see that my constants of proportionality cancel out. And so now what I have is just the ratio of the volumes is equal to the ratio of the lengths cubed. And so what I can do then is I can rewrite this solve for V large as by moving V small over to the other side. I calculated V small up above. It's the 0.09 3 ball 9688. L large is 10, L small was 0.281, and I cube it, and I come up with 43.7. I don't have to mess with calculating the constant of proportionality because the constant of proportionality cancels out when I take the ratio. So one of the features of scaling problems is I have to have enough information about one of the figures or one of the states to be able to calculate what I want to know, the volume or the area or another length. In this case, it's the volume. So I have to be able to calculate the volume of one, and then I have to have two lengths. In this case, it's L, in order to do the ratios. Okay? So let me present for you the general scaling principles after having done that example problem. It turns out that if I have two figures, and again, as long as they have the same shape but different sizes, like here, I've got an L1 and an L2, so the height of the cylinder is L here. Turns out that for volume, the volume is equal to a constant proportionality times any length dimension cubed. And so, in this case, L is the height of the cylinder. It could be L could be, I mean, the volume would be proportional to the diameter cubed. It would be proportional to one of these slant lengths cubed. It would be proportional to the circumference cubed. Any length dimension on these things, the volume of this, any volume associated with this figure is going to be proportional to any length on this figure cubed. Okay. It doesn't matter what the length is, doesn't matter what the volume is, as long as it's associated with these two figures. So what I can do then is I can write this as a proportionality, and then I can write the relationship just like I wrote in the previous example, where I can say the ratio of any two volumes, where I go from a large to a small or a small to a large or from one to a different one, is going to be equal to any length dimension cubed. And so that's effectively my starting point is really almost the very last equation here. So that's the way volume works. Turns out that I also can pick an area on here, any area measure. Let's say I pick the area of the end cap, which is the area of a circle, or it could be the lateral area of this thing, the pi dl. Any area, it doesn't matter. It could be the internal surface area of the cones. Any area I can write as an equation as being equal to a constant of proportionality times any length squared. It could be L, it could be the diameter, it could be the slant height of one of the cones. Any length if I square any length, it'll be proportional to any area on these figures. And I can do the same thing. I can write as a proportionality or as a ratio. And so if I know one area on one figure, and I know two lengths, one on each figure, then I can calculate the new area, just the same way I did the volume. Then finally, there's also a scaling rule for any length. That is, I can pick any length D. It's going to be proportional to any other length L. And so again, you have total freedom to pick what lengths you want here. It could be, the one length could be the circumference. The other length could be a slant height of one of the cones. Could be the height of the cylinder. Could be the circumference of the cylinder plus the height of the cylinder. Any length dimension, whatever you want, is going to be proportional to any other length dimension on these two figures. And again, I can write a proportionality, or I can write it as a ratio, which is really the starting point for most of these scaling problems. So those are the rules that we use. So we have volumes, we have areas, we have lengths, at least for the ones that have these geometrical effects. So let me work a problem here. So here's one that we had from earlier. I pulled it off some tests. Again, we have a very large number, I mean hundreds of these scaling problems from old tests. So here's one: a tree 10 feet tall has a trunk circumference of 18 inches. What's the height of a tree with a 25-inch diameter trunk? So what I've got here is I have two length dimensions, and I want to know another length. So I'm relating lines to each other. The only trick here is you have to be a little careful, because in one case I'm using a circumference, in the other case a diameter, to try and trick you up. So what we can do is I can say, in this case, any length on the object is proportional to any other length. So in this case, I'm relating the height of the tree H to the circumference C. I just pick the circumference. You can pick the diameter too. That works just fine. So in this case, what I do is I want to know the height of the new tree I call H2. The height of the old tree was 10 feet. That was given. The circumference of the new tree is actually pi times 25 inches, right? Because it's pi d to get the circumference. And the circumference of the small tree was 18. So it sets up this way. And I guess that's 18 inches in the denominator. So the inches cancel. I get feet, and it comes out to be 43.6 feet. So that's the way these scaling problems work. Again, the nice part about this is I don't have to make any assumptions about what the tree trunk shape is. As long as they have the same shape, I can work these problems. So in some cases, maybe more than others, sometimes it's kind of a stretch whether the two shapes are actually identical, and we'll see that as we go through today. But in this case, you can sort of assume that a tree that's 10 feet tall, a tree that's 43 feet tall, maybe we can certainly make an assumption that they have, nominally the same shape. Okay, well, let me look at another one. Here's another one that deals with area wall map. I got this wall map of Texas, scaled at 1,580,000. What that means is that basically 1 inch on my map is actually equal to 1,580,000 inches on the state of Texas. So if the area of the state is 267,339 square miles, what's the area of my map in square inches? So again, what I'm doing here is I'm relating two areas geometrically similar because they both have the shape of Texas, and I'm given a length dimension on both of them, but I get that from my scaling, 1 to 1,580,000, and I have the area of one, so I can get the area of the other, which is what we want to solve for. And again, I would mention here that this is a case where coming up with the constant of proportionality for the shape of the state of Texas is it's not impossible, but it's incredibly tedious to do. We'd have to make probably 100 measurements off of this thing and break them into primitives like trapezoids or circles or things, and it's just nightmarish. Whereas it's completely unnecessary when we use the scaling principles. So in this case, we start again with the area. This is the starting point for area ratios, where I have relate any two areas to any length. I'll let A2 equal the area of my map, which has the length associated of 1. The area of the state of Texas is the 267,000 square miles. When that's the length ratio on that is my 1.58 million inches in this case, or it could be whatever we want it to be. It could be feet or anything, but they both cancel. And so what I do is I simply move the area of the actual state over, and I calculate it out. It turns out that the area then A2 solves out to be 1.071 times 10 to the minus 7 square miles. And so then I have a couple of conversion factors, convert feet to miles to feet, and convert feet to inches. And I use squiggly brackets for the conversion factors. And I have to square that because it's square miles to convert to square feet to convert to square inches. And it comes out to be 430 square inches. So about 20 inches on a, sort of a 20 inch by 20 inch square-ish kind of for the shape. So again, this is a way that we can relate areas in geometrically similar figures using the lengths. Okay, so I can do let me work another one that's, this one's a little bit more complicated because we have to work with volumes and areas, which I haven't talked about yet. We've talked about lengths and areas, and lengths and lengths, and lengths and volumes. But here's a problem where we want to relate a volume to an area. So in this case, I have the material cost of an empty 12-ounce water bottle is 3 cents. That's for the container. How much does an empty 2-liter water bottle cost? And what we're going to do here is we're going to assume that the thickness of the bottle is the same and that it doesn't scale with size. And the reason I do that is because in reality, that's the way that these bottles typically are made, is they have a constant thickness, not which that is the 2-liter, the larger water bottle is not thicker than the smaller water bottle. So what I could do then is this. So the area of my water bottle, I'm talking about the surface area of the water bottle itself is proportional to L squared, and the length is proportional to the volume to the 1/3. Basically, I took the 1/3 power of my volume equation. And so when I combine these two, what I wind up with is that the area is proportional to volume to the 2/3 power, which is, again, it's any area and any volume. And so I assume that the area the container cost is going to be the area of the container, the surface area, times its constant thickness. And since T is a constant, A varies according to V to the 2/3. The cost is going to vary according to V to the 2/3 because area is constant. So, so we have that. So we have volume to the 2/3. So now what I can do then is to get the cost of the 2-liter container ratio to the cost of the 12-ounce container. It would be written this way: it's cost 2 over 3 cents is equal to the volume of the 2-liter container, 2 liters, over 12 ounces for the small one. Again, it's to the 2/3 power because I'm relating areas to volumes here. I've got a couple of conversion factors. I convert my liter to a quart and my quart to ounces. And so I have those conversion factors. Again, I have to raise it to the 2/3 power so I can cancel. Basically, I'm going to cancel liter to the 2/3 power in the numerator with liters to the 2/3 power in the denominator. So I have to raise my unit conversions on the right side to the 2/3 power. So I just multiply all this out. It comes out that the cost of the larger container comes out to be 10 cents. So again, so this is one of the a place where we can deal with. We can write areas as being proportional to volumes. I can also write lengths as being proportional to volumes. Then it's shown here. L is equal to v to the 1/3 power. In some cases, that's helpful to have. Okay, let me charge ahead. Here's a different kind of problem that is maybe one step removed from proportionality. There, I have some that are even more removed from this geometrical effect. This is a classic scaling problem. Goes all the way back almost to the beginning of the contest in the early 1980s, and it's scaling cooking recipes. So there's a million recipes out there. So there's a million scaling problems that you can write. So here we go with this. Let's read it. A recipe calls for 2 cups of flour to make 3 dozen, I think it's 2-inch diameter cookies. How much flour is needed to make 5 dozen 3-inch diameter cookies? And we assume that the cookie dough is rolled to a constant thickness regardless of cookie size, which is, I think, generally that's the case, that the thickness of the cookie is typically independent of its diameter. But that's not necessarily the case. I mean, I could, for example, have left that last sentence out and the problem would work just fine. In this case, the 3-inch diameter cookies would be a little thicker than the 2-inch diameter cookies, right? But in this case, they all have the same thickness. So what I could do is, again, I can start it with this proportionality, which is the number of cups of flour I need is going to be proportional to the number of cookies I want to make in times the diameter squared of the cookies. And again, this comes from the fact that, let's see if I have this here. No, it comes from the fact that it's diameter squared and not diameter cubed, because the volume of a cookie is going to be diameter squared times the thickness, and the thickness is a constant, so it drops out of the proportionality, right? I can effectively cancel the t out. So if I were doing this problem where the cookies actually did not have a constant thickness, my equation would be the number of cups of flour would be proportional to n times d cubed. But in this case, because the thickness is the same, it's really d squared t is the volume of one cookie, and so I can cancel the t out. I don't need it in the proportionality. And so basically what this is saying is the number of cups of flour is going to be equal to the number of cookies I want to make times the volume of one cookie. So effectively, what I'm saying here is that the number of cups of flour is proportional to the total volume of cookie that I want to make. So that's what we have. So then what I can do is I can say, okay, I want to know how much cookie dough I need to make 5 dozen 3-inch diameter cookies. So I'll let that be C2 is how many cups of flour I need. I divide it by what I know, 2 cups of flour to make 3 dozen 2-inch cookies. So you see all of those numbers in the denominator. I've got my 5 dozen 3-inch cookies in the numerator with C2. And the length dimension is squared because I'm dealing with an area on the cookies. So at the length, it's length dimension squared. Again, I'm dealing with an area because the thickness of the cookie is constant. Again, if that were not the case, that would be cubed. So anyway, so it's squared like that. So again, I just multiply it out. Turns out I need 7.5 cups of flour to get this cookie recipe going. Okay, so that's the way that goes. I've got a few more problems here to talk about. Here's a scaling problem with area. So if I've got this one, if the cloth cost for a pair of 18-inch waist blue jeans is $12, what's the cloth cost for a 40-inch waist pair of jeans? Well, again, in this case, I assume that the cost is proportional to the area because I'm assuming that the cloth has the same thickness, whether it's an 18-inch waist or a 40-inch waist. So same thickness, so the cost is proportional to the area in this case, which is proportional to L squared. And so the cost, and again, the cost is proportional to the volume, technically to the volume of cloth, but since the thickness is a constant, it's proportional to the area because the thicknesses will cancel. And so I have I write this equation, then cost 2 over cost 1 is L2 squared over L1 squared. So I can make my cost 1 is $12 for an 18-inch waist. My cost 2 is associated with a 40-inch waist, and I square the lengths because of scaling principles, and I come up with 59 bucks and 26 cents. I would remind you that on the calculator test for dollar problems, you have to answer the problem to the nearest penny, regardless. So, this doesn't round to 3 significant digits like most problems do on the test, and it doesn't round to $60 to $59 either, even though in the problem statement I have $12 with no decimal point or cents. Again, the answer must go to the nearest penny, regardless. Okay. Let's look at this one. Again, I just have a few more. I've got a couple of problems. Hopefully you have a calculator handy. I'm going to give you an opportunity to work some scaling problems, and then we'll see what the answers come out to be. Maybe I'll try and work them myself while you're working them too. So here's the one that deals with volume. So I got 4 equilateral triangles. I draw them on a sheet of paper. I fold them up to make a pyramid. The volume of the pyramid is 8 cubic inches. So if I reduce the paper size on a copier by 47%, what's the volume of the resulting smaller pyramid? Well, it still has the same shape, so I can use scaling principles. In this case, what we can do is, in this case, it's a volume being proportional to length dimensions. I have to be a little bit careful because it's my volume 2 could be let's see how I do it. Volume 2 is going to be the smaller one. The volume 1 will be the larger one, the 8 cubic inches. So my length dimension is the smaller length, but again, it's not 0.47, it's 0.53 because I'm reducing it by 47%, which means what I have left is 53%. So it's 0.5, so 1 inch would go to 0.53 inches. So again, I have 0.53 and then 1 for my ratio of lengths, and I cube that. That gives me the means to solve for V2. And the V2 actually becomes really pretty tiny, 1.19 cubic inches. I would have guessed a bigger number than that based on the 8 cubic inch starting point. But I guess, one way to think about it is I reduce it by a factor of 2, just about crudely about 50%. And so it'd be 0.5 cubed would be 1/8. So that would give me 1 cubic inch. So I guess that seems reasonable then. Okay. Well, I've got a 3D printed artwork here. Some of you may know that I've spent my research career doing 3D printing or additive manufacturing. This is where my real expertise lies in terms of my career. And so this is close to my heart. And so we have this one, a 3D printed artwork. I show an example here, 14 inches long and weighs 4 pounds, 3 ounces. How long is the same artwork built larger that weighs 17 pounds? So again, in this case, what we have is it's not volume, but we have mass. But what I can do is the mass I can write typically as being equal to some density rho times the volume. So effectively then, I'm assuming that the density of the plastic in the small piece is the same as the density of plastic in the larger piece, rho becomes a constant, and my mass is proportional to V, and V is proportional to L cubed, so my mass is proportional to L cubed. And so we have this, so I can write the masses now. The mass ratio is being proportional to a length ratio cubed. And then what we do is I can take my 17 pounds is the larger mass. My smaller mass is 4 3/16 of a pound. I convert the ounces. My larger length is what I want to solve for. The smaller length is 14 inches. I cube the length dimensions because of scaling principles, and then just multiply everything out, solve for L2, and it turns out the 14 inches increases to 22.3 inches. And then there we go. Okay, well, there's some other problems that get a little more complicated. This is a very simple one that's actually quite complicated, I think. At least it shows some new principles here. It takes 38 blows to inflate a balloon to 14 inches. How many more blows are needed to inflate it to 18 inches? And so in this case, we have no idea what the shape of the balloon is. It turns out that if you have students that want to brute force a problem like this, what you could do is you can, because the shape doesn't matter as long as it's the same for each of the states at 14 inches and 18 inches, you could assume a cubic. If I were doing it in brute forcing, I would assume a cubic balloon because it doesn't matter what the shape is, or you could assume a spherical balloon if you want to. And the other thing that we have to assume is that the volume that I'm increasing the balloon by every time I blow into it is the same, which for a balloon, I think that's really a pretty good assumption because it's working against one atmosphere and the elasticity of the balloon, which I don't think is that great. So again, those are the assumptions we're making, is that every time I blow into the balloon, I'm actually injecting a constant volume into the balloon. Okay, so here's the way we do this thing. The total volume of the balloon then is going to equal the number of blows times the volume of one blow. And because the volume of one blow this is going to be proportional to any length dimension on the balloon. And so that's how I get my 14 and 18 inches. And so what I can do, since I have this, I can write the ratio is that the ratio of the total volumes is going to be the ratio of N2 to N1 times the volume of a blow divided by a volume of a blow. And so VB2 and VB1 are equal to each other, right? Because the volume of one blow is going to be the same. So I get just in the number of blows, then N2 over N1 is going to be proportional to L2 over L1 squared cubed. So now what I can do is I can solve for the number of blows based on the information I have. So the number of blows to inflate it to 18 inches is given by this equation. I take the number of blows to get to 18 inches is equal to 38 blows. And then that's equal to 18 inches divided by 14 inches. So again, the 18 inches is associated with the larger balloon. The 14 inches is associated with the smaller balloon, where I got with 38 blows. And then I have a cube there. So I get the number of blows to inflate it to 18 inches is 80.8 blows. But this is the tricky part about this problem, is that's 80.8 is not the answer. That's the number of blows it takes to inflate an initially uninflated balloon to 18 inches, but it takes 38 blows to get it to 14 inches. So the total number of additional blows after 38 is the difference there that you see. So basically, to answer the question, how many more blows are needed to inflate a 14-inch balloon to an 18-inch balloon, is actually 42.8 blows. And again, we would answer this to 3 significant digits. And, certainly there's nothing improbable about or unlikely or unrealistic about having 8/10 of a blow. I could certainly at least do something that would come close to that, at least in principle. So again, we're talking 42.8 more blows to make it work. Okay, this problem, here's a problem that's perhaps one of the more complicated ones in scaling principles. I thought I would maybe end with a hard one here. I think this is my last problem before I give you a chance to work some. So here we are. So what I've got is we can look at this. I guess I'll skip this. I got 5 pounds of pebbles that are 0.1 inch long. So that gives me the size of these pebbles. I don't know how many I have, but I know that I've got 5 pounds of them, and they're 0.1 inch. Each pebble is 0.1 inch long, and it's got a certain total surface area of all of the pebbles. So I take my 5 pounds of pebbles. I measure the surface area of one of those pebbles, then I count all my pebbles up into 5 pounds and multiply that surface area of one pebble times n, the number of pebbles I have in the 5 pounds, and that gives me a certain surface area, total surface area. And then the question is what mass of 0.01 inch, presumably long, sand is needed to provide the same total surface area? And the assumption here is that the shape of the sand and the shape of the pebbles is identical, so I can use scaling principles. That's the assumption we make here, which is implicit. So the way that this problem works is since I don't know the number of pebbles, I have a little bit of work to do here. So what I can write is the total mass of the pebbles, or really of the sand even, the total mass, m sub t, is going to be equal to the number of pebbles, or the number of pieces of sand, times the mass of one pebble or one piece of sand. So in this case, I could write that as being equal to the density times the volume of one particle, either one pebble or one piece of sand. And so I have this because the density, again, I'm assuming that sand and pebbles have the same density, so I can get rid of that. So the mass is going to be equal to proportional to the number of particles that I have times a length dimension cubed. Well, what I can do is I can solve that for n. Well, this is the tricky part. I solve that for n, it's going to be the total mass divided by the length cubed. And so I can write that either for the sand or for the pebbles in this case. So now to get the surface area, the total surface area, so I put, just sort of put that aside. Let's start over here with the surface area. That's going to be equal to the number of particles I have, either of pebbles or sand, times the surface area of one pebble or the surface area of one little particle of sand. And again, the area is proportional to L squared by scaling principles. So now I've got, so my area is proportional to NL squared. But what I can do is I can take N and write it out. I write the number of particles or number of pebbles I have as a function of the mass by substituting in that first equation, N is proportional to MT over L cubed. I substitute that down below for N. So I have MT over L cubed times L squared, or my surface area actually goes as the mass divided by the length, where it's linear length. So what this says is if I double the mass, I double the surface area. That makes sense. But if I double the size of the particle, my surface area will actually decrease by a factor of 2. And again, that's because I'm adding more. If I make the length bigger, I get more surface area, but I have fewer particles, right? And the surface area goes as L cubed. The number of particles goes as the inverse of L cubed. I mean, so let me say that again. The number of particles goes as the reciprocal of L cubed. The surface area of one particle goes as L squared. So basically, as my particles get bigger, I get, for the same mass, I get less surface area. And so that actually is reasonable. So now I can write the equation this way. I can say my A2 over A1, where A2 is going to be the unknown in this case. And A1 is going to be mass 2 over L2. Then I have to divide by total mass 1 over L1. So I flipped it up into the form you see here. And so what I've got is my mass, the total mass 2, which will be for the sand, divided by the particle size of the sand, which is 0.01 inches, is going to be, I multiply it by L1, which is the particle size of the pebbles, 0.1 inch, and the mass of the pebbles, which is 5 pounds. And because they have the same surface area, my A2 over A1 is equal to 1. And so now I have one equation I can solve for the total mass. It turns out that the total mass is only a half pound. So basically, as the particles get finer, I can get away with a much smaller mass to get the same surface area. Because as the particles get smaller, the specific surface area actually goes up. So I only need a half pound of sand to get the same surface area. This type of problem is not completely esoteric or hypothetical. It turns out that there's a whole world of problems associated with catalysts and with manufacturing where I have to have a certain surface area in order to have enough active region to affect some change, which is, say, some kind of catalytic change. And so the surface area is important because the surface area defines the rate of the reaction in the catalytic case. So yeah, we would do these types of problems. All right, here's maybe perhaps the last problem I have for you is it's the pitch of a bell. This is one that's perhaps the furthest removed from a geometrical similarity. I think I have one more problem after this actually that's also like this. So I'm talking about the pitch of a bell. It's inversely proportional to the diameter of the bell. And so in this case, I don't know anything about the shape of the bell. It's the pitch, which goes as a reciprocal of the diameter. And so this is just a straight proportionality. There's no geometry because there's no geometry associated with the pitch or the frequency of a bell. Okay, so that also, it turns out that an octave higher pitch has double the frequency of the lower note. So the question is what if a 5-inch diameter bell is pitched at middle C, what's the diameter of a bell pitched at high C, which is 1 octave higher, which would have double the frequency. So in this case, what I do is I start with my, in any case, I'm writing a proportionality. So in this case, the frequency or the pitch is proportional to the reciprocal of the diameter. So F goes with 1 over D. I can write as an equation as F2 over F1 is going to be D1 over D2 effectively, right? Because it's a reciprocal relationship. I substitute in the numbers. My new frequency is twice the original frequency because it's an octave higher. So F2 is equal to twice F1. So I have 2F1 over F1 is going to be 1 over D2 times 5 inches over 1. Because my original bell has a diameter of 5 inches. So I have one of the F1s, of course, cancel. I can solve for D2. And I wind up with D2 is equal to 2.5 inches. So I reduce the diameter by factor of 2 to increase the pitch by factor of 2. So what are the rules of this? So one of the more generalizations is for bells. For any bell, if I want to go octave higher or an octave lower, I have to simply change the diameter accordingly by a factor of 2, either 2 times larger or 2 times smaller. So I multiply by 2 or multiply by a half, depending on whether I want to go to a lower pitch or a higher pitch by 1 octave, respectively. All right, I think this is really the last problem I have for you. This one is again deals with proportionalities without really much geometry involved. So this is one with a reading light. I have Sonny reads by a 100-watt light that's 2.5 feet from his book. How close should a 50-watt light be to his book? And then I acknowledge the reality that light intensity is actually inversely proportional to the square of distance, because basically the intensity, I could imagine that the intensity of the light has to be spread over a sphere of diameter d, depending on where d would be the distance from the light bulb. So as I go further and further away, the intensity doesn't drop linear; it actually drops by a factor of distance squared. So what I can do then in this case is I can say that the intensity this is the intensity at the reading surface where Sonny wants to read. That's going to be proportional to the intensity of the bulb divided by d squared, the distance from the bulb. So again, if I kept the 50-watt light bulb at 2.5 feet, he would have half of the brightness, right? So the intensity at the book goes as proportional to the intensity of the bulb to the 1 power linearly. So based on this, I can write a ratio that looks like this. The intensity 2 over intensity 1, which is equal to 1, because we want him to have the same reading brightness on the paper. So the two intensities at the paper are going to be equal to each other. That's going to be an initial intensity 2 over d2 squared times d1 squared over the initial intensity 1. So we can write it this way by saying that 1's going to be equal to, say, 50 watts over d2 squared, where d2 is what I want to solve for. And then for my d1, I have a 100-watt bulb that's 2.5 feet apart away. So it's going to be 2.5 feet squared over 100 watts. The watts cancel, and so I can solve for d, and it comes out to be 1.77 feet. So again, I can do a sanity check. Obviously, if I reduce the intensity of the bulb, I have to move it closer to the reading surface. That seems reasonable enough. And then we go from 2.5 feet for the 100-watt lamp to 1.77 feet for the 50-watt light bulb. So again, this is a demonstration of scaling principles. It's still scaling because basically I'm writing relationships that have a proportionality. And I can, just as before, even with geometrically similar figures, there would be, if we wanted to brute force this and could dig up enough information, I could come up with a constant of proportionality that would change that proportionality in the first equation I wrote, namely this one. I could change that proportionality to an equal sign and calculate the constant proportionality if I had enough information, but it's not necessary because of the scaling principles. So I can get away with it this way. Okay, so that's I took about 45, 50 minutes. So now here's a chance to work a problem. Give this one a shot. A Chihuahua dog, 7 inches tall and weighs 2.5 pounds. What does a 25-inch tall Great Dane dog weigh? So again, what we're assuming here is that a Chihuahua and a Great Dane have the same shape. I mean, I think to a first order, that's probably pretty good. I'm looking at the figures here. They seem to be, sort of reasonable. It's not perfect, but maybe good enough for an approximation. So if you have a calculator, why don't you go ahead and chug this one out and see if you can't figure out how much the Great Dane weighs. And I'll tell you what the answer is, but I'll give you a second to calculate it, and I'll tell you how I would go about getting an answer in a sec. And if you're brave enough to post an answer, feel free to throw one up in the chat if you want. See what you get. I mean, nobody's getting graded on this, so it doesn't really matter. So I think that hopefully maybe that's enough time. Again, I didn't put the solution here. I just have the answer. But the way we would do this is, again, because the volume scales with the mass for these geometrically similar figures. What I can say is that the weight of the Great Dane divided by the weight of the Chihuahua, 2.5 pounds, is going to be equal to the quantity 25 inches over 7 inches cubed. So the answer would be I take 25 over 7, cube it, multiply by 2.5 pounds, and hopefully I'd get the answer, which would be 114 pounds, which I think probably is about right. Great Dane is a really big dog. And so typically most of the big dogs that I deal with run around 80, 85 pounds, but a Great Dane's a really big dog. So I think this is pretty reasonable. And I'm sure I sanity checked the answer as well to make sure the Great Danes fall in this range. Okay, let's try another one. How about this one? An 85-pound girl needs 2 square feet of material to make a hat. How much does a woman weigh if she needs 3 square feet of material to make her hat? So why don't you give that one a try? And by the way, I'll give you a hint. We're going to assume the material has the same thickness, because I think that's a good assumption based on reality. So what we, in this case, what we have is we have the area is proportional, goes with length to the 1/2 power. And we got this, the mass of the girl goes with the weight of the female goes with length cubed. So what we do is, I guess we would take 3/2 square feet. I take the square root of that and then cube it, and which would be, in that case, I'd be 3 over 2 to the 3/2 power times the 85 pounds, I think will give me the weight of the female. And when I multiplied it out loud, I got 156 pounds, which seems like a reasonable weight for a woman. So that's that. I think what we'll do is, well, I'll give you this. I think hopefully you can access these slides. We won't go through this one in any detail, but basically this is just a recipe problem that I threw out with the complication that you want to know the number, how much butter, but it's how many packages do we need to buy. But you can hopefully access the presentation and work it. Again, you have to assume that the butter is the amount of butter I need is going to be proportional to the number of scones and to the length dimension cubed, because in this case, the scones will have the same volume, the same shape, though they will not have the same thickness. That is, the 3-inch scone will be shorter or less tall than the 4-inch scone. So in that case, it would be, I guess, it would be 450 over 450 divided by 8. And then I would have 3 over 4 cubed, and that would be equal to the cups of butter divided by 2 cups. No, cups of butter divided by 8 cups. I'm sorry, 3/4 of a cup. I'll get it right. So then I can come up with the number of cups I need. Then to get the packages, I have to acknowledge there's 2 cups in a package. And it comes up, the answer I got was 9 packages. And again, in this case, we have to round up to the nearest size of butter. So yes, that takes me to the end of this. I think what I can do is, by everyone's leave, let me stop sharing this so I can get back to David. And maybe, I don't know if people have been posting anything in chat. So there's 43 44. So maybe David, I don't know, maybe you can uh, go through and sort of sort through these. Oh, people are posting answers. Good for you. Lots of right answers. So David Trussell, do you want to try and read these, or do you want me to just sort of poke through these and find them myself?
So I think we've everything that was prior on the chat list has either been answered or was just was not an actual question. So we do have one though that's just come in. So we know that number 46 on every test will be a scaling problem. About how many total scaling problems are expected on one test?
Yeah, there's I think there may be. I mean, if you look long and hard, and again, I'm only referring to the test I write. I write 9 tests every year, so historically that's been the case, which is 3 tests for UIL competition. That's district, region, and state, and then I write 2 invitational meet tests for the UIL. That gets me to 5, and then the 4 remaining is 3 invitational meet tests that go to the TMSCA, and then the TMSCA has, at least historically, has had an open state meet the week or 2 before district UIL district, and so I'll write that test. So it's 9 tests that I write. If I think if you look hard and heavy, you may find a second scaling problem on a test, but I would say that's probably 1 in 100 tests. So to answer the question, it's 1. You expect 1 on each test, and it will be sitting in problem 47. So you can just take that to the bank, but that's what you'll see. So let's see, will the PowerPoint, contain explanations? Oh, for those 3 at the end, no, I didn't, but Alicia, what you can do, and this is open to everybody on the list. If you can persevere and find my email address, which I think is at the UIL website in academics, or again, you just Google my name and you'll find me at the University of Texas, and my email address is on the website for me. If you could find an email address for me, and I don't know, I guess I can post. Let me see. Let me just do it here. You don't even have to look. I'll just type it here and put it in the chat box here.
I just added that too.
Oh, okay. Yeah, there it is. Right. Yeah. So just for anybody, really, this applies to this session. It applies to life in general. You know, you get into school next year. Heaven help. Hopefully there will be school next year, and hopefully there will be UIL events this next year. But if you have really questions about anything, you want a problem solved, have a question about the rules, just feel free to shoot me an email. I'm happy to answer those. If it gets to the point where you're asking me to work, 5 problems every day for a week, I may start to balk. But that, at least in the 30-something years that I've been doing this contest, that's never happened, and I don't anticipate that it will. So feel free to shoot me the emails, and I'm happy to work those. And as well, again, if you have problems you want to solve, I mean, I particularly appreciate them now, because on the 13th of July, I'm just going to go in and do an open problem solving session. It's going to be a real short session if I don't have any problems to work. So getting some problems from you would be really, really cool. So feel free to email me. And if you want solutions to these 3 problems, I'm happy to do those. I'll work a solution out and email them back to you. Be happy to do that. So let's see. Okay. Oh, you want there's a question for you, I guess, David. Can we get a recording from last week's session?
We
the one that
we are going to be posting recordings. We're working out the logistics of that because of the number of sessions we have and where we're going to store all that video. But we are working on that, so there will be an archive of conference sessions posted later in the summer.
Yeah. And by the way, just if I could, let me just emphasize, I don't have access to the recording, so I can't really help you with that.
All right. If we don't have any other questions, thank you to everyone for attending today. Thank you, Dr. Bourell, for the great presentation. We have additional STEM sessions coming up on a variety of topics. We have more sessions on our science contest. In addition to Dr. Bourell's problem-solving session, Larry White is doing a math and number sense problem-solving session, also in July on the 10th, I believe. We have sessions on robotics and computer science as well. So keep checking the schedule for updates and additions. And thank you again for joining us today, and have a great afternoon.
Yeah. Thanks, everybody.